Hey, ChemStars, this is Mrs. Vanderwally bringing you Chapter 11, Gases and the Kinetic Molecular Theory. I just want to preface this saying that this is probably one of my favorite chapters to teach. There's a lot of really cool stuff that we can do with gases and the kinetic molecular theory. I think that this unit really explains a lot of what we would observe around us, if you're observant. So I'm hoping that you will treat these videos that are coming for Chapter 11 with that kind of an attitude like, yeah, I can relate to this. I understand this. This makes sense to me. So anyway, that's my preface. Hopefully you have your notes in front of you. If you don't, get out a piece of paper and jot down what we're doing. All right. So we're going to start off with gases and pressure. So we need to begin and talk about what is pressure. And we're going to use the kinetic molecular theory as a basis for what is gas pressure. Okay. So the kinetic molecular theory, okay, is a model for gases, okay? Kinetic, what does kinetic mean? So we have, kinetic means motion. So we have kinetic energy that you should have learned maybe in physical science that talks about the energy of motion. So what is the kinetic theory? Is the fact that all gas molecules are always moving. Okay, think about that. All gas molecules are always moving. When do they quit moving? At absolute zero, which, folks, we have never achieved here on Earth before. Okay, so that means for all of our reality that all gas molecules are moving. Okay, what else do we assume? That particles in a gas are considered to be hard, small spheres with a very insignificant value. So they're just really teeny tiny. And we will just kind of think of them as hard spheres, not as what we think of with a nucleus and electron clouds and all that kind of stuff. So that's going to kind of come into play a little bit later. And it says that the motion of the particles in a gas is rapid, constant, and random. What do I mean by random? That means you're just going in a straight line at a constant speed, if you will. And nothing is going to deter you from the path unless you hit something. All right, so there's no giant magnet to lure you away from that constant path, that straight line motion. And then it says all collisions between the particles in a gas are perfectly elastic. And what does that mean? That means that you don't lose any energy when they collide. Okay, so if you don't lose any energy, that once they hit something, either the wall or the inside of a balloon or another gas molecule, that the energy they went into that collision is the same energy as they come out of that collision, so they don't lose any of that. And how do I know that that is true? Well, if you think about it, just as a conservative estimate, if the Earth is, let's say, 10,000 years old, all right, some people think it's actually not that old. Other people think it's older than that, okay? So let's just say 10,000 for a random number. So if the Earth is 10,000 years old and those gas molecules have been moving and colliding for 10,000 years, don't you think by now that if they lost energy with each collision, they would quit moving at this point? Yeah, probably so. All right. But the fact is that here we can breathe. We breathe gases. There's things called gas pressure, still exists here today. So to me, that's a pretty compelling reason saying that, yeah, these collisions are perfectly elastic. Okay. So what is gas pressure? This is what I want you to think about. That gas pressure is a result of simultaneous collisions of billions of rapidly moving particles in a gas with an object. So what word do I want you to think of as far as gas pressure goes? I want you to think of the word, here we go, collisions. That's the word I want you to think of, okay? So air pressure is the collisions of atoms and molecules in air with objects, okay? So let's talk about air pressure. All right, this graph here is very important. Okay, so jot this graph down or fill it in if you have your notes in front of you. So what does that mean? That at 30 kilometers, and I'm going to show you why in a minute, At 30 kilometers, that is considered where 99% of all our atmosphere is located. So you take the Earth, go 30 kilometers away, all right, straight out, all right, away from the Earth. And if you had, some way to measure it, you have 99% of the atmosphere, 99% of all the gas molecules will be within that 30 kilometers. But then if you go down to 5.6 kilometers, which isn't that far away, all right, some of you may only live 5.6 kilometers away from Oak Hills High School. Okay, so it's not that big of a distance. Half of our atmosphere is located in the first 5.6 kilometers. Okay, why is that? Well, as altitude increases, there are fewer gas molecules. But wait a minute, Mrs. Vanderbilt, you said 90% of our atmosphere is 30 kilometers. That's higher than 5.6. That's right. So down here, the first 5.6 is half our kilometers, all right, or half of our atmosphere. And then it kind of thins out, if you will, as you get closer and closer to 30. So why is that? Well, it has to do with gravity. All right, so what does that tell you? Well, gases must have mass, all right? So if I have fewer gas molecules, that means what? Go back to this word collision. If I have fewer gas molecules, are there going to be more or less collisions? There's going to be less collisions, therefore pressure will decrease, okay? So here's a little tidbit, something to think about. Why are there dead bodies on Mount Everest? If you want to try to Google this trying to breathe on Mount Everest Nova video, they say that there are dead bodies if you walk around, the path to climb Mount Everest. Well, why do they die? Well, they can't breathe. So why don't they do something about it? Well, if it's difficult to breathe at the altitude of Mount Everest, you're not going to carry this dead body down the hill with you. You're probably going to die too, all right? So why don't they just, bring an airplane up and put the dead bodies on the airplane and let it take it? No. Why can't they take an airplane on that? Well, there's no place to land, but there's not enough air. All right. How about a helicopter? Helicopters can land on a very small, place, right? Well, how does a helicopter work? Those blades are pushing down on the air pushes up on the blades, and that gives them lift. But there's a problem. There's not enough air molecules, gas molecules to push down on to give that helicopter lift. A helicopter cannot make it to the top of Mount Everest. So there's really not a whole lot they can do with those dead bodies on Mount Everest. All right, so they just kind of leave them there, sadly. All right. And another one is why are there more home runs hit in Coors Stadium? Well, where is Coors Stadium? Well, that's in Denver. And when I wrote up these notes, there was an article in the Cincinnati Enquirer saying that Coors Stadium at this time had more home runs than any other stadium per time period. Well, why is that? Well, where is Denver? It's in Colorado. It's pretty high up, isn't it? What does that mean? Well, if it's high up, there's not as many gas molecules there, right? So if you hit that baseball pretty hard, there is fewer gas molecules to cause friction to slow it down so it can go further. Okay, so these are some kind of, facts about our atmosphere, and think about that for a minute, okay? So, all right, let's go on. Let's define gas pressure and calculate the various pressure units. We're going to talk about torr and kilopascals and millimeters of mercury and atmospheres and things like that, okay? So let's check this out. Once again, let's repeat this. Gases are always moving and colliding. They're going to be colliding on you, on the walls, inside the balloon, inside and outside of a tire. Remember that gases have mass. We talked about that because that's why they're affected by gravity. And they have velocity. Therefore, they have kinetic energy. Do you remember what kinetic energy is? 1/2 mv squared. So we have mass and we have speed, okay? And these moving molecules are colliding, and this is cause pressure. So let's go to the next page. Okay, so what is pressure? Well, pressure is force per area. And you might remember that force is equal to ma, right? Well, what's that? Mass times acceleration. So if you are running and you're accelerating, you can exert force. But what about me, who I'm just sitting here? All right, do I still have force? Yes, I do. I have weight. All right, so I take my mass, and the acceleration is actually the acceleration due to gravity, and that defines my weight. So we can talk about force as being a weight divided by area. Now, the SI unit, the Système International, if you want to go French on me, all right, unit of force is a Newton. Yeah, it's named after Sir Isaac. And then the unit for area is meters squared. So think of a big block, all right? And that is how we define a Pascal. Okay, so let's talk about this idea of pressure and force and area real quick. So if a person who's accidentally walks on the thin ice on a lake can lower the risk of falling through by lying down on the ice. Why? Well, think about that. Think about what I just said, and maybe you come up with your answer first. All right, what would happen if I was standing up? All right, if I'm standing up, all my weight is on my feet, which has a smaller surface area. So here's my weight over a small area, pressure goes up. You're going to fall through. But if you lie down, your weight is distributed over a larger surface area. So if surface area gets bigger, pressure goes down, and you're less likely to fall through. What are some other things you can think about? Oh, I remember when my kids were little, we were reading some kind of like a magazine for kids, and they were talking about, I remember, like, mountain lions. And did you know that mountain lions have unusually large feet? All right. And the magazine went on to say, well, why do you think they have such large feet? Well, they're going to have more surface area, so they're less likely to be sinking down into the snow. All right, so they're more mobile that way. Okay, so again, something to think about. All right, so units of pressure. Okay, so here we go. On a typical day at sea level, the air exerts a force of about 100,000 newtons. All right, and then it says a 30-kilometer tube on each square meter of your body. This resulting force of 101,300 pascals or 101.3 kilopascals. Okay, where did that come from? It came from up here. All right, so newtons, 1 newton over a square meter. Well, if I had 100,000 newtons over a square meter, that'd be 100,000 pascals, okay? This pressure is equal to 1 atmosphere. But wait, the weatherman doesn't report weather with atmospheres or kilopascals. The pressure from your graph, if you made a graph, that is about 760 millimeters of mercury, and the weather reports in inches of mercury. So let's see where all these numbers are coming from, okay? So I found a picture of the Earth, and then these are all the different layers of the different atmospheres, if you will. Okay, so here's the troposphere, and notice this says 30 kilometers. I don't know if you can see the little numbers, but that's our 30 kilometers. And the troposphere is really defined as where the gas molecules are. And then there's a stratosphere you may have heard of, and a mesosphere, and a thermosphere, and an exosphere. That's all great. Satellites are floating around there. I'm most interested in this troposphere. So if I have this 30-kilometer tube, all right, so I'm going to blow this up. All right, this is our atmosphere, right? So I'm going to blow up this tube. You ready? So here is my same 30-kilometer tube of air. Here it is. Okay, and there's gas molecules in it. Now, how handy is a 30-kilometer tube of air? Not very. Okay, not if I want to work with it. Okay, so I need to find something more dense than air that will shrink this tube to something more manageable. All right, so why don't I use water? After all, don't you think that water is a pretty common thing to deal with? So if I had a 30-kilometer tube filled with air, all right, as our atmosphere, it'll have the same mass as roughly a 10-meter tube of water. Okay, so this is my air tube, this is my water tube. All right, now if you think about 10 meters, folks, that's taller than your average room. Okay, I know my room, my classroom, is about a little over 3 meters tall. Okay, or just under, I'm sorry, just under 3 meters tall. So I'm talking about roughly a 3-story building is roughly 10 meters. So if I have the same circumference tube 30 kilometers tall, that is the same mass with air as the same, diameter tube, but only 10 meters of water. Now, how handy is this 3-story tall tube? All right, is there a whole lot I can do with it? No, I need to find something even more dense than water. So what those scientists did back in the day said, oh, mercury, it's a liquid and it's pretty dense. Mercury is actually 13.6 times denser than water. So if I were to divide this 10 meters by 13.6, guess what? I get about 760 millimeters, which is about 700.76 meters of mercury. So that's what this 760 millimeters of mercury. So what am I saying? This 30-kilometer tube of air has the same mass as a 10-foot tall of water, has the same mass as 760 millimeters of mercury. Folks, that's less than a meter. This is much more handy, if you will. You can actually hold it if you need to. Now, here we are in the U.S. Do we actually use much metric system? The answer is no, we don't. So what we do is it's the same mass, same height, but the units is 29.92 inches of mercury. And I showed the work down here. So how many inches is 760 millimeters? Well, there's 10 millimeters in 1 centimeter. 2.54 centimeters in 1 inch, and that's 29.92. So when the weatherman is reporting what is the barometric pressure, all right, he's going to do it in inches, or she is going to do it in inches of mercury, all right? And it's that same idea as millimeters of mercury that we're going to use. And where did it all come from? Our 30 kilometers of air. Now, in case you are wondering, how much does this weigh? Well, when we're talking about the 10,000 newtons, which is, 10,000 kilopascal or 10,000 pascals, they were saying that this down here was 1 square meter. Well, that is a huge tube. Okay, I'm sorry, that's a huge tube. So what if I made this 1 square inch? I think you can all figure out what a square inch looks like, okay? So if I had 30 kilometers of air with a square inch at the bottom of the tube, has the same mass as 10 meters of water with a 1 square inch, which is same as, less than a meter, okay, 760 millimeters of 1 square inch, it would weigh 14.696 pounds, okay? So the mass of all 3 tubes would be roughly 15 pounds per square inch, okay, which is 14 point roughly, 7 psi's. Okay, so that's where these numbers all come from. So let's go back and fill in our chart. All right, so let's go back. So what did we learn? If we looked at that Earth picture, that 30 kilometers represents 1 atmosphere. Okay, that's our troposphere. All right, and so we defined, about 100,000 newtons. All right. Well, to be more exact, it was 101,300 pascals. What's this divided by 1,000? 101.3 kilopascals, okay? And then what? Well, again, that tube wasn't too handy. So I divided the density of water by the density of air, and it ended up being about 10 meters tall. Remember that? Now, notice that this is not bold because you will not see this in any kind of a conversion, okay? But that's how we went from really atmospheres to millimeters of mercury, okay? So here is that. Remember, I showed you how they got that. They took the density of mercury and worked with it. Now, there's an Italian physicist. I don't think his name is Tortellini, but it's something along those lines. All right, Torricelli, I think. And I guess he wanted to be famous. I don't know. And these two are identical. And then I also said that this is your inches of mercury. Okay, and I already showed you how we got that. So now we want to convert between units. So I kept these up here, all right? And you don't need to memorize this, but I think it's interesting to know where it all came from. If you ever need these conversions, they'll be given to you, so don't panic. All right, so let's just practice this. You're going to have to know how to do this. Your homework will have you do this. So how many atmospheres are in 750 millimeters of mercury? All right, so we're going to factor label this, all right? So how many atmospheres are equal to, well, I want 750 millimeters of mercury. So what goes on the bottom? Millimeters of mercury right here. Okay, do you see that? So that's where I put my 760. And what am I looking for? These are all equal to one another. So what I'm looking for is 1 atmosphere. Remember, that was our troposphere. And if you want to, get out your calculator and calculate away. And what do you get? I got this. But wait a minute, what's about my sig figs? I only got 2 sig figs here, don't I? So I only need, the 0 doesn't count, so 9, 8, what do I have to do with the 8? Oh, I need to round up, don't I? So it's 0.99 ATMs, okay? Right number sig figs. So why don't you take a minute out and try the next one? How many atmospheres are there in 98.9 kilopascals? Go ahead and pause this and try that. All right, welcome back. Let's see how you did. So how many atmospheres are in 98.9 kilopascals? Well, what unit do I want? I want atmospheres. What do I need to get rid of? Kilopascals. Well, here's my kilopascal. See that? So that number goes on the bottom. And I do want atmospheres, so that goes on the top. And remember, my units will cancel out. And that leaves atmosphere behind. So when I calculated, I got this. But how many sig figs do I have? 1, 2, 3, right? 0 doesn't count. 1, 2, 3. Do I round up? Nope, the 3 doesn't round up. So I got 0.976 atmospheres, okay? Well, we have only a little bit more to go. And John Dalton, I don't know if you even remember John Dalton. He's the one that we learned about in one of those videos from way back when. And he helped us understand things about the atom and whatnot, all right? So he was pretty decent dude there, all right? He came up with a whole bunch of stuff. So Dalton's law of partial pressure says if a container contains several different gases mixed together, the pressure, this is important, of each gas is called the partial pressure. So what did Dalton do? Okay, he said that the total pressure is equal to the sum of the partial pressures. So the total pressure is the partial pressure of A, gas A, whichever that is, plus the partial pressure of gas B, plus the partial pressure of gas C, if there is a gas C, plus however many gases are there. So it's pretty easy. I think you can do this. So a balloon is filled with a pressure of 99.5 kilopascals with 2 different gases. We have nitrogen and oxygen. We only have 2 gases, okay? So if the pressure of nitrogen, if the partial pressure of nitrogen is 33.6 kilopascals, what is the pressure of oxygen? Well, here we go. Pressure total is equal to pressure of A plus pressure of B. This is Dalton's law of partial pressure, isn't it? All right, what can I fill in here? Well, do I know what the total pressure is? I do. Do I know what my 2 gases are? Yeah, nitrogen gas and oxygen gas. Okay, so now let's plug in some numbers. My total pressure is 99.5 kilopascal. My pressure of nitrogen is 33.6 kilopascal. So what's the pressure of oxygen? Well, what am I going to do? I'm going to subtract 33.6 from both sides, and I get 65.9 kilopascals. Yes, folks, it is that easy. Now, I just want to caution you real quick. What if this were in kilopascals? And what if this were in, let's say, millimeters of mercury? What would you have to do? I bet you'd have to convert, like what we did up here. Okay, so just be aware, you might have some questions like that on your homework. And so this is probably one of the longer videos. I apologize for that, but there's a lot of really interesting information in this. So I will leave you with this. Don't wait to be great. We'll see you next time. Bye-bye.